Imagine a monster that was so powerful nothing could escape it. Now imagine that this monster was invisible and had the ability to freeze time and could stretch your body as thin as spaghetti. This might seem like a terrifying nightmare, but such monsters exist in our universe and they're called black holes. Join us as we journey through the cosmos to understand what black holes are, how they form, and why they could lead to the destruction of everything as we know it. Before diving into the science behind black holes, we need to discuss what a black hole is and how they form. This will provide the foundation for understanding what happens to matter and energy that fall into a black hole. Simply put, a black hole is a region of space where matter is packed so tightly together that its gravitational force becomes stronger than any other force in that part of the universe. This means that if anything, including light, gets close enough to a black hole, there is no escaping its gravitational pull, and it will be drawn toward the center, or what's known as the singularity. This is where the gravity of a black hole is most intense. We'll go more in depth into the different parts and aspects of black holes, but for now it's important to know that the singularity is where matter is compressed into an infinitely tiny point, and everything we know about time, space, and reality breaks down. The second part of the black hole we need to define is the event horizon. This is the boundary around the black hole where it becomes impossible to escape the gravitational pull produced by the singularity, as the velocity needed to break free exceeds the speed of light. And since the laws of physics tell us that nothing can move faster than the speed of light, there's no hoping to exit the black hole once an object gets past this point. The first person to describe a black hole was a religious man in England by the name of John Michell in 1783. Michell was considered a brilliant scientist at the time, however his ideas eventually fell into obscurity since the math and understanding of physics necessary to explain how a black hole works wouldn't be invented for another century and a half. In 1915, when Albert Einstein came up with his theory of general relativity, he predicted the existence of black holes based on the equations that he invented. At this point, the scientific community was divided on whether such a powerful and terrifying source of gravity could actually exist. But as cosmologists and mathematicians began to investigate the universe using Einstein's equations, it became clear that black holes were indeed theoretically possible. Then, in the early 70s, British astronomers Louis Webster and Paul Merton at the Royal Greenwich Observatory and Thomas Bolton, a graduate student at the University of Toronto, independently announced that they had discovered an invisible massive object orbiting a star over 6,000 light-years from Earth. The celestial body was emitting massive amounts of X-rays, but the source of the radiation could not be seen. The astronomers named the mysterious object Cygnus X1, which would eventually be regarded as the first black hole ever to be observed by scientists. It's worth mentioning before we go any further that a light year is the measurement of distance and not time. When scientists use the term light year, they're talking about the distance that light travels in one Earth year. Since light always travels at the same speed of 299,792,458 meters per second, or about 186,282 miles per hour, one light year is approximately 5.88 trillion miles, or 9.46 trillion kilometers. This means that 6,000 light years is around 30,000 trillion miles. Let's now discuss how these incredible marvels of space actually form. Even though we know the basic properties and physics of black holes, there's still a lot that scientists have yet to uncover. We know that most black holes are formed when a large star goes supernova and collapses in on itself. In the middle of stars, elements are being forced together in a process called fusion. Initially, the hydrogen in a star fuses together to form helium. After the star uses up all of its hydrogen, helium begins to fuse into carbon. This process continues until the fusion of elements start to produce iron and nickel. At that point, the fusion process no longer releases energy, instead requiring an input of energy to keep going. This causes the star to cool, leading to the outward forces of pressure slowly dropping. When this pressure drops to a low enough level, gravity takes over and the star collapses in on itself in a matter of seconds, resulting in a supernova explosion. In order for a star to go supernova, it must have a mass approximately 3 times greater than our Sun. Once these massive stars spew their elements across the cosmos, all that remains is an infinitely dense point in space, and this is how a black hole is born. However, the collapse of stars cannot account for every black hole in the universe, and this is where scientists are stumped. It's not entirely clear where some of the largest black holes in our cosmos came from. In December of 2004, astronomers observed flashes of light coming from a series of gamma-ray bursts The data collected suggested that these flashes were the afterglow of a gigantic explosion that resulted from a black hole and a neutron star colliding. This event resulted in a significantly larger black hole forming, which confirmed that black holes are not only created by the collapse of massive stars, but much larger black holes can be born from cosmic collisions. The largest black holes in the universe can be found in the center of galaxies and are known as supermassive black holes. The craziest part is that even though scientists know these are the most massive and densest black holes in our universe, they still don't know exactly how they were formed. We'll look more closely at each type of black hole to better understand what makes them different from one another, and hopefully gain a little more insight into where they came from. But before we do this, let's address some common misconceptions about these cosmological monsters. Black holes are not the same as wormholes. Sci-fi epics love to include wormholes that can take space travelers from one point of a galaxy to another in a matter of minutes. This is very important when writing exciting plots, because no one would want to watch a show or read a book depicting a crew traversing the cosmos at light speed and arriving at their destination hundreds of years after they left. Wormholes fix this narrative problem, as theoretically speaking, they can be used as a kind of space shortcut by folding space-time. The way this could work is that 2 points in the universe could be connected by a tunnel that has an entrance in one region of space-time and an exit hundreds, thousands, or even millions of light years away. To visualize this better, let's say you were a small insect on a piece of paper, and you wanted to crawl from one end of the paper to the other. Under normal circumstances, you need to crawl across the entire page to get to your destination, which could take a very long time. However, if the goal is to get from one edge of the paper to the opposite edge, and we fold the paper in half, you would only need to take a few steps to reach your destination. This is similar to how a wormhole might work in our cosmos. The 2 points in space-time could be folded on top of one another, and the wormhole would allow you to pass from one point through the fold to the other point. Unfortunately, black holes do not do this, because they are completely different phenomenon than wormholes. Instead, if you entered a black hole looking to take a shortcut between 2 points in space, you would be swallowed up by the singularity and crushed under its immense gravitational force. As far as we know, there is nothing on the other side of a black hole. Once you pass the event horizon, you're dragged into the darkness with no way to escape. Another common misconception is that black holes are the vacuum cleaners of the universe, sucking up anything and everything into them as they stalk the cosmos. In reality, black holes don't suck anything in. Instead, objects fall into black holes when they're put on a trajectory that brings them too close to a black hole's gravitational pull. Entire stars, solar systems, or galaxies orbit black holes in the same fashion that planets of a solar system orbit their star. And just like asteroids or any cosmic body that gets knocked off course, entire solar systems can end up on trajectories that bring them into the path of a massive black hole. Due to our universe's chaotic nature, things are always being knocked into black holes. For example, Sagittarius A, the black hole in the middle of our Milky Way galaxy, is constantly devouring stellar dust, celestial bodies, and stars. Some incredibly interesting and destructive phenomena can occur depending on what falls into the black hole. As some objects are ripped apart and consumed, they release huge amounts of energy and matter that are hurled across the universe. This can lead to a phenomenon known as relativistic jets, which shoot gamma radiation at near the speed of light out from a black hole, decimating anything in their path, including stars and planets. Typically, astronomers classify black holes in one of three categories: stellar mass, supermassive, and intermediate mass. There are no exact parameters for each set class, and there are black holes that straddle the line between the two groups. In fact, scientists are constantly reassessing and shifting the boundaries of each black hole type. Relatively recently, a fourth category called primordial black holes has been added. Let's examine each one to get a better understanding of the diversity within these phenomena and how it affects the science that goes on with them. Stellar mass black holes. Not all stars that go supernova end up as black holes. Depending on the mass of the star, it might not have enough matter to create a singularity, and instead just ends up as a husk of its old self, known as a neutron star. Neutron stars are super dense celestial bodies that have enormous amounts of gravitational pull, but not enough to form a black hole. The mass of our Sun is approximately 1.9891 times 10 to the 30 kilograms, or about 4.384 times 10 to the 30 pounds. This is approximately 333,000 times that of the Earth. A star needs to be around 20 times more massive than our Sun to turn into a stellar mass black hole, rather than a neutron star when it goes supernova. Stellar mass black holes can continue gaining mass as more matter falls into them. Since we cannot directly observe black holes, the only stellar mass black holes that we know of are paired with stars. The black hole pulls gas and matter from the nearby star, which forms into a disk around the event horizon. The gas becomes superheated and begins to produce X-rays, giving this type of interaction the name X-ray binaries. We know of around 50 suspected stellar mass black holes in our Milky Way galaxy alone. However, there are likely many more stellar mass black holes left to be discovered, as scientists believe there might be as many as 100 million in our galaxy. Supermassive black holes. Astronomers have found that practically every large galaxy in the known universe has a supermassive black hole at its center. Unlike stellar mass black holes that have a mass dozens of times greater than that of our Sun, supermassive black holes have a mass hundreds of thousands to billions of times larger than our Sun. These are enormous beasts that exert an immense amount of gravitational pull on the solar systems in the center of galaxies. Sagittarius A, the supermassive black hole at the center of our Milky Way galaxy, is approximately 4 million times the Sun's mass. However, this is relatively small compared to the black holes at the center of other galaxies. Take Holmberg 15A, a galaxy that lies around 700 million light-years from our own. Its supermassive black hole is at least 40 billion solar masses, or 40 billion times more massive than our Sun. Again, scientists are not entirely sure how these gigantic black holes came to be, but it likely had to do with multiple larger black holes colliding and combining their mass, while also consuming huge numbers of stars, planets, and space debris. It's hypothesized that some of these black holes formed in the first few billion years after the Big Bang, when the most massive and hottest burning stars went supernova. It's been suggested that since these types of stars burned through their fuel and exploded so quickly, sending their stellar guts across the cosmos, the resulting black holes had a head start on gaining mass. The fact that they've been around so long has allowed them to consume more matter than most other black holes, and thus become larger and larger, like the supermassive black hole that sits at the heart of Holmberg 15A. Intermediate black holes. Since there was such a big gap between stellar mass black holes and supermassive black holes in terms of size, scientists created a third classification known as intermediate black holes to fill the gap, which covers black holes with a mass of over 100 times that of our Sun to tens of thousands times the mass of our Sun. Intermediate black holes have already consumed large amounts of matter and may have even combined with other black holes, but they're not yet large enough to be considered supermassive. Over time, as intermediate black holes devour more and more matter and continue to collide with other black holes, their mass could become large enough to bump them into the next category of supermassive black holes. Interestingly, scientists are still debating whether any intermediate black holes have actually been discovered. Theoretically, intermediate black holes should be fairly common in the cosmos, as stars are dying and going supernova all the time, resulting in stellar mass black holes forming. Since the universe isn't stagnant, each stellar mass black hole will eventually begin to consume nearby matter and anything that crosses into its domain, starting the evolution from a stellar mass black hole into an intermediate black hole. The fact of the matter is that intermediate black holes are likely lurking in the darkness of space and don't have excretion disks or neighboring stars to help scientists locate them. They're also not quite massive enough to exert their gravitational influence in a noticeable way, such as with supermassive black holes, which again makes them hard to locate. Regardless, astronomers are still on the hunt for these bridges between stellar mass and supermassive black holes. Primordial black holes. The final classification that scientists use for black holes is primordial black holes. These are black holes that formed seconds after the Big Bang. It's believed that as the universe was born from the original singularity, some of the matter might have been hot and dense enough to immediately form black holes. Scientists theorize that these very early black holes could have had masses that ranged from 100,000 times less than a paperclip, making them micro black holes, to 100,000 times more than the mass of our Sun. After the Big Bang, the universe quickly cooled, and the formation of primordial black holes ended. These black holes would have already been consuming matter and growing hundreds of millions or even billions of years before the first stellar mass black holes even formed from stars going supernova. To be fair, primordial black holes are only hypothetical, as scientists believe that our universe is around 13.7 or 13.8 billion years old, and there is currently no way to know what happened moments after the Big Bang. Some cosmologists have proposed the idea that primordial black holes, and all black holes for that matter, might have a lifespan, and due to quantum mechanical processes, may eventually evaporate out of existence if there isn't enough matter around them to consume. Smaller black holes are predicted to evaporate more quickly than larger ones, but either way, the remnants of many primordial black holes may have disappeared from existence long ago. Let's now dissect black holes even further and examine the inner and outer workings of these cosmological mysteries. But first, let's discuss something that must be on everyone's mind. What would happen if you were to fall into a black hole? Since no one has fallen into a black hole yet, scientists have to theorize what would happen. But using the laws of physics, we know that some pretty astonishing and gruesome things would happen if you cross the event horizon. Let's start with spaghettification. This is the technical term for what would happen to you or anything else that fell into a black hole and was pulled toward its singularity. Imagine you were floating toward a black hole. You're feeling just fine until you start closing in on the event horizon, where gravity is so intense that nothing, not even light, can escape. As you get closer to the singularity at the center of a black hole, the gravity becomes more and more intense. The problem is that this is happening extremely quickly. There are massive differences on how gravity acts across every centimeter of your body. For a few seconds, your feet are being pulled toward the center of the black hole quicker than the top of your head. Your body would begin to stretch. This might feel good for a split second. It would straighten out your spine and stretch your muscles. However, as you approach the event horizon, the gravitational pull becomes so intense that it would literally stretch your body out into a thin noodle shape. This is where the aptly named term spaghettification comes from. So from your perspective, you would survive until part of your body approached the event horizon of the black hole, and then a few seconds later you would be dead as your body stretched into human spaghetti. However, things get even stranger for someone who is watching you fall into a black hole from far away. As you approach the event horizon and gravity increases, time seems to slow down. To the observer, you would seem to be moving so slowly that it'd be hard for them to tell if you were moving at all. In fact, once you hit the event horizon, you would seem to stop moving completely. This means that to an outside observer, you would be alive just before the event horizon practically forever, because it would take many of their lifetimes before your body would pass beyond that point and disappear into the singularity of the black hole. Eventually, you would just disappear from the observer's perspective, but it'd take a very, very long time. This all has to do with the perspective and what Albert Einstein called relativity. Basically, the more gravity there is, the slower time moves for you than someone who's observing you where there's less gravity. So if you were to fall into a black hole, you would be spaghettified, frozen in time, and destroyed all at once, depending on what perspective you were viewing the interaction from. Needless to say, things get really weird the closer you get to a black hole. Even though the masses of the black hole are all different, the anatomy of a black hole, regardless of size, is essentially the same. A black hole only possesses three basic properties, which limits how different any two black holes can be from another. These three distinguishing properties of black holes are mass, spin, and electrical charge. Let's see how these three properties impact how black holes interact with our universe. As we mentioned earlier, the event horizon is the boundary around the black hole where the velocity needed to escape the gravitational pull exceeds the speed of light. The very fact that nothing, including light, can escape the black hole once it reaches the event horizon means there is no way for an outside observer to see or know what happens past that point. The only way to definitively solve that mystery of what happens inside a black hole is to pass the event horizon and observe what happens before you're turned into spaghetti and crushed. However, any intrepid astronaut who embarks on that journey in the name of science will not be able to send a signal out of the black hole. So whatever is seen in the milliseconds before death will only be known to the person who has passed the event horizon, which kinda defeats the purpose of entering the black hole for science. Even though black holes themselves don't emit or reflect any light, astronomers can see where the event horizon is. This is because any object that's pulled into a black hole will seem to freeze in time just before the event horizon due to gravity's effect on relativistic time. What this means is that supermassive black holes that have consumed hundreds of thousands or millions of stars appear to have objects endlessly circling the event horizon even if they've already fallen into the singularity, as time seems to stop due to the immense gravity at the center of the black hole. Just outside the event horizon is the accretion disk, another part of a black hole that scientists can observe. As black holes consume stars, they pull the gas away from the stellar bodies. This gas settles into a very hot, very bright, rapidly spinning disk around the black hole known as an accretion disk. This gas and any other matter caught in the black hole's gravity well is pulled toward the event horizon and allows astronomers to see the boundary between the accretion disk and the event horizon. Unfortunately, not every black hole has an accretion disk, as it needs to be actively consuming a star or some other celestial body. Due to the gravity of black holes, the accretion disks have a very unique shape. The gravity warps the fabric of the universe, which means that any of the light from the accretion disk must follow that distorted path. This results in a phenomenon known as gravitational lensing. The light that passes over the accretion disk from behind the black hole bends, forming a hump over the top and the bottom of the black hole. The shape changes slightly depending on the angle at which the accretion disk is being viewed. If you're looking at the black hole straight on, the accretion disk has no hump at all. A phenomenon known as the event horizon shadow results from distortion of space-time by gravity around the event horizon. This too causes gravitational lensing of light, which, combined with the warping of time-space, results in a dark zone around the event horizon, which ends up being around twice as large as the black hole's actual surface. The corona of the black hole is considered one of the most extreme environments in the universe. Strong magnetic fields form a storm of superheated gas and matter between the inner accretion disk and the outer edge. The corona temperature is believed to be as high as 1 billion degrees Celsius. This intensely hot gas and anything in it orbits the black hole with a velocity reaching the speed of light. Due to its violent nature, the black hole's corona is the main source of X-rays due to an incredible amount of energy being generated. One of the most striking and little understood parts of a black hole is known as particle jets. For some unknown reason, material in the accretion disk being pulled toward the event horizon will suddenly be blasted away from the black hole in two jets pointed in opposite directions. Relativistic jets are one type of this phenomenon. The particles are fired at just under the speed of light. The particle jets of supermassive black holes can extend for hundreds of thousands of light years, obliterating anything in their path. Then there is the singularity. This is the very center of the black hole, where matter is crushed to the point of infinite density. The singularity will be the final point where matter that passes the event horizon ends up. It's unclear if a black hole's singularity is a physical structure or just a mathematical one. The closer you get to the singularity, the more our conventional understanding of physics breaks down. It's believed that at a certain distance from the singularity, relativity stops altogether, and unknown quantum effects take over. At this moment in time, there's no way to know exactly what happens at a black hole singularity, but scientists are continuously trying to make sense of these incredibly strange phenomena in our universe. This brings us to how we know what we know about black holes. It's estimated that around 10 million rogue black holes are cruising around our galaxy. The first astronomers to discover black holes did so by observing the cosmos and looking for clear byproducts of those cosmic monsters. As stars, planets, or anything else in space approaches a black hole, its gravity acts upon that object in dramatic ways. Astronomers can observe black holes throwing celestial bodies off their natural orbits. For example, stars behaving strangely or orbiting a seemingly empty region of space might suggest that there is a black hole present. Just by observing the orbits of stars around a black hole, scientists can calculate the mass of the black hole. In fact, that's how Nobel Prize winner Andrea Ghez and her team first detected the supermassive black hole at the center of our galaxy. Scientists can also see the light of stars and gases bend around the gravity of black holes. These phenomena provide evidence that there is a black hole nearby. Observations such as these and advancements in telescopes have allowed scientists to both indirectly and directly view black holes in our universe. Astronomers have also recently developed methods for detecting black holes from the gravitational ripples in space-time that they cause when they collide. This signal can actually tell scientists how much mass the black holes had, how far away from Earth the collision occurred, and how fast the black holes were traveling when they smashed into one another. Interestingly, black holes closer to home might actually be harder to detect. Let's imagine a scenario where the path of our own solar system was on a collision course with a black hole lurking in the darkness of space. As mentioned before, there are likely millions of black holes that cannot be observed by astronomers due to the fact that they're in empty space where nothing around them emits light. In this scenario, we wouldn't know there was a black hole nearby until it was too late. The first indication that a black hole was entering our solar system would occur when outer planets were pulled from their orbits. We'd watch as Uranus and Neptune disappeared into the maw of a black hole. The scary thing is that Earth wouldn't even need to be pulled toward the event horizon to erase humanity from existence. Just having one of these cosmic monsters in our solar system would launch planets off their orbits around the sun. Earth could be slingshotted out into the void of space, where the planet and everything on it would freeze to death. Luckily for us, we don't need to worry about this occurring, as scientists estimate that the chance of a rogue black hole passing by our solar system is around 1 in a trillion. The nearest known black hole to Earth is 1A06200-00. Luckily for us, close is a relative term. In fact, that black hole is around 3,000 light-years away. So this particular black hole is not a major concern for Earth at the moment. Astronomers have also been able to locate a black hole from the oldest parts of our universe, labeled 0313-1806. This black hole is around 13 billion light-years away, meaning it must have been formed no later than 13 billion years ago. The largest black hole that has ever been observed has been aptly named TUN 618 and has a mass around 66 billion times that of our Sun. Cosmologists have labeled the fastest spinning black hole that we know of as GRS 1915+105, which rotates around 1,000 times per second. That means by the time we finish this sentence, the black hole has spun around approximately 8,000 times. So this brings us to one of the biggest mysteries in science. What is actually inside of a black hole? The short answer is scientists just don't know. This is due to the fact that traditional math and science break down once you get past the event horizon. However, there are some theories of what might happen just past the maw of these cosmic behemoths. Many scientists believe that as something gets close to the singularity of a black hole, quantum effects that we just don't know about yet begin to take over. Could this cause the matter that falls past the event horizon to end up in another quantum realm or a universe altogether? Scientists can't even begin to make predictions due to the fact that we don't know what forces are at work near the singularity. There's evidence to suggest that all of the matter being incorporated into the singularity will eventually become so immense that the black hole itself could explode. However, physicists have noted that it could take billions and billions of years for this to happen, even to the oldest black holes. Some scientists believe that the information pulled into black holes might be stored in the singularity, while others think that somehow the information is destroyed and gone forever. The science of black holes is fascinating because we know a decent amount of what goes on around a black hole, but absolutely nothing about what happens inside of one. Perhaps in the future, humanity will have the tools and math to finally unravel the mysteries of black holes. That is, if our solar system isn't devoured by a hidden black hole in the darkness of space first. Now watch how humanity will actually colonize Mars year by year, or check out what is a white hole opposite of a black hole.